NASA is working on revolutionary propulsion technology that will enable us to reach Alpha Centauri in just 40 years. Currently, however, the dream of interstellar travel still seems like an impossible wish, thwarted by the vast distances of space. But in the future, the Sunbeam propulsion system is expected to accelerate a research probe to 10% of the speed of light, bringing it within reach of previously unattainable star systems. But how does it work? What technical tricks will make the endless vastness of space a thing of the past? And will trips to distant stars and exoplanets soon be part of our everyday lives? Be sure to stay tuned until the end and see for yourself the groundbreaking concept NASA is using to usher in the era of interstellar space travel. Signs of life on another world. It's news that couldn't be more spectacular. The James Webb Telescope has recently confirmed that dimethyl sulfide actually exists in the atmosphere of the exoplanet K2-18b, a molecule that is produced exclusively by organisms on Earth. This is by far the strongest evidence of extraterrestrial life found to date. According to experts, the oceans of this alien water world could even be teeming with life. Now imagine that we could send a research probe to K2-18b to conclusively confirm the existence of our long-hidden contemporaries, and possibly even capture them on camera. After all, this extrasolar world of desire is only 124 light-years away from us. And what's 124 light-years? Well, in astronomical terms, no more than a stone's throw. But for space travel, this distance unfortunately still represents an insurmountable hurdle. A single light-year is an inconceivable 9.46 trillion kilometers. And although the Voyager probes have been flying through space for almost 50 years, they haven't even covered a single light day yet. And that's not because the aging probes are creeping through space like slow snails. In fact, their traveling speed is around 61,500 kilometers per hour. But 61,500 kilometers per hour is simply not enough to make the leap to exoplanets or alien star systems. And that's putting it mildly. Because K2-18b is by no means the only celestial body out there suspected of harboring a groundbreaking secret. In fact, astronomers have already identified a whole series of potentially habitable exoplanets in our cosmic neighborhood. Proxima b, our closest hope. One of these planets is practically right on our doorstep. Discovered in August 2016 and located in the constellation Centaurus, Proxima b is only 4.2 light-years away from us. The planet orbits its autonomous red dwarf Proxima Centauri, which in turn forms a triple star system with the binary star Alpha Centauri. Since Proxima b is the closest known exoplanet to Earth, it's also the most obvious target for the first interstellar mission of all time. The sobering news, however, is that with our current resources, it would take 70,000 to 80,000 years for a probe to reach Proxima b. But in the future, and this is the crucial point, thanks to unprecedented propulsion technology, we could succeed in dramatically shortening this journey time and finally make the dream of interstellar travel a reality. How NASA's Sunbeam propulsion system works. When it comes to speed records, there is currently no way around the Parker Solar Probe. NASA's Icarus recently reached an incredible speed of 692,000 kilometers per hour, flying faster than any other man-made object before it. But let's be honest, what is 692,000 kilometers per hour compared to 100 million kilometers per hour? What at first sounds like a crazy speed straight out of a science fiction movie is actually the realistic travel speed NASA is aiming for with its Sunbeam concept. That's equivalent to 30,000 kilometers per second, or about 10% of the speed of light. At that speed, the Alpha Centauri system would no longer be tens of thousands of years away, but only 40 years, beaming through space. So how is that even possible? Basically, the idea behind the Sunbeam drive is astonishingly simple. Instead of providing a space probe with fuel for its journey at launch, it is to be supplied with the necessary energy from outside during its mission. The role of this permanent filling station is taken over by an external platform, which ensures a constant supply of energy via a particle beam. Let's be clear, the aim is not to send a puny mini-probe to distant stars and planets, but a full-grown 1,000 kilograms research probe, equipped with all the latest instruments. The real heart of this innovative propulsion technology is the relativistic electron beam. These are electrons accelerated to nearly the speed of light, generating enough power to propel a spacecraft across interstellar distances. This beam is to be generated by a solar statite, a stationary satellite near the Sun that hovers in place with the help of radiation pressure and solar magnetic fields. From this position, it fires the high-energy electron beam at the probe. The solar statite transfers the impulse that constantly accelerates the spacecraft, without it having to rely on its own fuel. The longer the beam acts on the probe, the greater the speed boost. A focused beam in the vastness of space. Wouldn't the electrons eventually disperse in space? After all, they usually repel each other. Fortunately, we know of a physical solution, the pinch effect, aided by Einstein's theory of time dilation. Put simply, time appears to pass more slowly from the perspective of a moving system. In the case of sunbeam, time dilation helps keep the relativistic electrons from drifting apart, allowing the beam to remain focused even over extreme distances. Advantages over other concepts. If this ambitious idea becomes reality, we would be able to venture into interstellar worlds for the first time within a realistic time frame and verify whether exoplanets live up to their reputation as potential cradles of life. This also applies to Proxima b. While the planet likely has tidal locking, dividing it into a cold night side and hot day side, it orbits within the habitable zone. This zone allows for liquid water to exist, and it's conceivable that a twilight zone exists between the two extremes, where cool water flows. The truth is, we simply don't have enough data yet to know if that's the case, or if life has already developed on Proxima b. An interstellar space probe could answer that question on site. Other concepts, like breakthrough starshot, approach interstellar travel differently. Launched by visionaries like Stephen Hawking and Freeman Dyson, this initiative proposes tiny probes the size of microchips, equipped with light sails and propelled by giant laser arrays. By contrast, Sunbeam proposes a more economical and powerful solution, a single solar statite and a full-scale probe, offering more functionality and scientific potential than a tiny chip. When will it happen? Unfortunately, we'll need to be patient. Sunbeam, while promising on paper, involves completely new propulsion technology that must be developed from scratch. That includes the electron beam itself and the requirement to precisely align it with the probe over interstellar distances. Even a small misalignment would cause the beam to miss the spacecraft and end the mission. Moreover, the beam will require increasing amounts of energy to remain effective over distance. And since the solar statite will be stationed near the Sun, we'll need materials that can withstand extreme heat and radiation. The technology gap. Many core components of Sunbeam are already theoretically feasible. For example, the Large Hadron Collider at CERN can already generate beams with more energy than Sunbeam would require. The beam guidance systems of modern particle accelerators could be adapted for precise targeting in space. And if we look at the Parker Solar Probe, we've already developed craft that can survive close proximity to the Sun. However, the thermoelectric generators needed to convert solar heat into electricity exist only in theory. We currently lack the technology to make these extraterrestrial solar power stations a reality. Developing them will take time and money. Timeline. Even the most optimistic forecasts suggest it will be at least 20 to 30 years before a Sunbeam prototype can be launched. However, our most optimistic forecast is that it will take no more than 20 to 30 seconds for you to subscribe. Click the thumbs up and hit subscribe so you never miss another cosmic update from us. We'll see you soon.